So now I'll look at an example that demonstrates a context-sensitive pointer analysis and how it operates and what are its strengths and limitations. Okay, so and the example I'm going to take is this example where a compiler tries to optimize a program by resolving the virtual function calls at compile time. So I'm considering an object-oriented language, and consider this base class in this object-oriented language like C++ or Java, where the base class contains a virtual function, and in this case it's an abstract function, which means that the derived classes will have separate implementations. Let's say there are two derived classes, D1 and D2, and they both have separate implementations of this function f, this member function, this virtual member function f. And now I'm going to show some code which is going to have some aliasing behaviors, and then the compiler will be compiler would be interested in identifying whether a certain object is definitely D1 or definitely D2. If the compiler can at compile time definitely say that some object is D1, and let's say the function f is called on that object, so let's say there's some object x on which f is called, and the compiler can reason at compile time that x definitely is D1 and not D2, then x can just resolve the virtual function call directly to D1's f. So recall that virtual function calls are actually resolved at runtime, because depending on what object it is being called on, the corresponding function is called. So if it was at runtime, the system checks, or the program checks, whether the current object, the receiving object, is a D1 type or D2 type, and depending on that, it will call D1's f or D2's f. But if the compiler can at compile time resolve this and say that no, this is definitely D1's f, then it can avoid the overhead of the runtime lookup in the V table to do this resolution at runtime. And so this is an optimization where the compiler tries to resolve virtual function calls at compile time. Okay, let's look at an example. So let's say there's another class copy that just has a single function, copy is small case, which just takes an input argument of type base, which could be either of type D1 or D2, and then returns a copy of the incoming object. So it just takes B and returns B. Okay, and let's say this is my main function. It creates a new copy object. So C is equal to new copy. Then it creates a new base object X, but so it creates a new D1 object. It creates a new D1 object, and then calls C pointer.copy on it. So this is going to just take new D1, put it into as an argument to copy, and then that's what it's going to return. So X is going to have a pointer. X is going to have a copy of D1. I'm using a mixture of C++ and Java syntax, because when I say new D1 and base B, just consider that base B is a reference, and when I return B, then that's the reference that's returning back. So think of this as a reference, and new is creating a reference. And when I say this arrow is similar to dot in Java, and in C++ it's an arrow, which basically calls the copy function on the reference C. Okay. So base x equals c dot copy new d1 is just going to, as we can see, copy is just going to return the reference. So that's just going to give put x equals whatever was allocated at d1. And similarly, y equals c dot copy new d2. That's going to put d2 in y. So when we reason about this program manually, then we can clearly see that x will be pointing to a d1 object and y will be pointing to a d2 object. And then if you call x.f, then d1's f should be called, and when you call y.f, then d2's f should be called. But we can do this kind of reasoning manually, but the question is, can the compiler do this kind of reasoning in a general setting? And we are going to use our pointer analysis, our context-sensitive pointer analysis on this program to see whether it can do this or not. Okay, so the first step in doing the context-sensitive pointer analysis is to label the allocation sites and the call sites. So one allocation site is this new copy, so let me call that LC. Another allocation site is this new D1, let me call this LD1. Similarly, another allocation site is new D2, let me call it LD2. Moreover, these sites, I'm kind of skipping a few steps. I should have actually expanded this into 3 address code and then done all this, but just so that I can fit everything on a single slide, I'm avoiding that step, and it still works. So the same label LD1 is both an allocation site and a call site to this function copy. And the call site recall is important for the call context, for our context sensitive pointer analysis. Okay. And so this is LD1, this is LD2, and the question is which f should be called, which f is called, can we resolve this at compile time? Can the compiler resolve this automatically at compile time? Now, this is the top level function main, so I'm going to assume that the initial context is 0. So now I'm going to just use my transfer functions for a call context point analysis. I'm going to use Anderson's analysis. It doesn't matter, the same call context sensitivity can be applied to Steensgaard algorithm as well, or any other representation of the points to graph. But I'm going to use the Anderson's algorithm because it's the simplest thing. So here I'm analyzing, so this whole body of main is being analyzed in context 0. So when I transfer across this instruction C equals new copy, this is the allocation rule gets triggered, and so the corresponding object is the corresponding abstract object is denoted by LC in context 0, so that becomes LC0, and that gets assigned to C in context 0, so that's C0. So I say C0 may point to LC0. So this becomes my edge in the points to graph as I'm executing my points to algorithm. I also want to emphasize that I'm going to execute this algorithm at call context depth of 1. And later I'm going to discuss what is the effect of increasing the call context depth, etc., and what are the implications of using a single depth. Of course, we have seen previously that if we increase the call context depth, then the number of call contexts can increase. In general, it can be exponential in the depth because if you look at the call tree or the call tree or the call graph, then the more depth you have, the more kind of paths you will potentially have. Okay, so this is the first edge that I have in my points to graph by virtue of this allocation statement. Now I'm going to continue this. So there's an allocation statement new D1, and that gets the object, the reference that gets created here is copied to the argument of the copy function, which is B, and B will be analyzed in the call context LD1 because we are using a call context depth of 1, and we kind of go through this, we reach copy through this call site. So the call context depth becomes the call context becomes LD1, and 0 gets removed because the actual call context, the full depth call context would be 0 and LD1, but because we are using a depth of 1, so the call context becomes LD1. Okay, so let's look at this. So because of the virtue of this statement here, we basically the dispatch of the copy function, the new D1 is basically represented by the abstract object LD10 or LD10 because it's a new allocation at allocation site LD1 in context 0. So that becomes LD10, and that gets copied to the argument B, and the argument B is being analyzed in call context LD1 because of the virtue of this dispatch. And so B in context LD1 may point to LD1, the allocation site LD1 in context 0. So this is my new edge by virtue of this call. Once again, B is in context LD1 and the allocation site is in context 0. And so the allocation site itself is called LD1. Because I'm using the same LD1 for both the call context or the call site and the allocation site, the LD1 is appearing both as a call context and as an allocation site. So I hope that's not confusing you. All right. Now, when the function copy gets called, it just simply returns B. B was already pointing to LD10. So this return value gets copied to X. And X is being analyzed in call context of main, which was 0. So we draw another edge which says X0, because that's what at the return time we apply the copy rule, because the return value gets copied back to the call site at in the returned register. So the returned register is X0. So X0 now points to whatever B was pointing to, and B was pointing to LD10. So X0 is also may also point to LD10. So this is the points to graph that gets created by virtue of the first two statements in the program. Now I similarly analyze the third statement in the program, and I'm going to do something similar. The third statement is almost identical to the second statement. So this is what the call context graph would look like. Just like I had L0 D1 for new D1, I'll have L0 D2 for this new D2, and because the allocation site is LD2, the B this time will be analyzed in call context LD2, so it becomes B LD2, which is different from B LD1. This is the versioning of the B variable depending on the call context in which it's being analyzed, and B LD2 may point to L0 D2, and this is the precision improvement. I'm going to discuss this more later. And then when it gets returned back to Y, then Y0, because Y was being analyzed in context 0, may point to whatever B LD2 may point to because by virtue of this return. Then that means Y0 may point to L0 D2. And this is my, you can check that this is the final points to graph. This is a fixed point. You can rerun the algorithm. You can check all the instructions again and transfer again, and you would find that this is a fixed point solution. And because it's a fixed point solution, I know that x.f can only point to L0 D1. So x can only point to L0 D1, which is of type capital D1. Similarly, Y0 or Y in context main can only point to L0 D2, which is of type D2. So I can resolve these f's precisely by saying that this should simply call D1's f, and this should simply call D2's f. In other words, the compiler is able to resolve the virtual function calls at compile time and thus save runtime overhead, runtime vtable loop overhead due to due to the general resolution at runtime, how it is done. Okay, so this is an example of context sensitive pointer analysis being used to resolve virtual functions at compile time. Okay, now I just want to say that if I was instead using a context insensitive analysis, then the results would have been imprecise, and we can just see why. Well, if the context was imprecise, or context was insensitive, then I wouldn't have versioned B based on the call site. So recall that I was basically versioning B in two ways, B LD1 and B LD2, depending on which call site I was called from. But now there will be a single B variable, which will be the argument here, and that B may, by virtue of the first call, it may point to LZ. By the virtue of the first call, it may point to L0 D1, and by virtue of the second call, it may point to L0 D2. And then when you return B, then it seems like X may point to either L0 D1 or L0 D2, because X is just going to get a copy of B, and because B may point to either of these, X may point to either of these. Similarly, Y may point to either of these. And so this is the final points to graph. X seems like it may point to either L0 D1 or L0 D2, and Y seems like it may point to either L0 D1 or L0 D2. And this is imprecise because now the compiler cannot reason that this F is definitely D1's F, because it may point to either D1 or either a D1 object or a D2 object. And so in this case, this is a context, in this example, a context insensitive analysis will not be able to resolve these virtual function calls at compile time. Whereas a context sensitive analysis with a call context depth of 1 was able to resolve these virtual function calls at compile time. Now let's take another example where even if I use a context sensitive analysis of depth 1, I would not be able to resolve the virtual function calls at compile time. And I don't have to do much. I still use the same base D1, D2, which have a virtual function f. D1 and D2 have separate implementations of f base. In the base class, the f function is not defined. And then I have a copy function copy class just like before, but this time the copy function calls another function, which I call the helper function. And when somebody calls copy on some object B, then it just calls helper on that B and returns that value back. And helper does what copy was originally doing, which was just copies D just returns the reference to the input one. Just returns the input argument D. Now notice that all I have done is I've increased the depth of my call stack by introducing another helper function that helps copy. And because of that, my call context depth of size 1 will be insufficient, as I'm going to show you. So once again, I label all these allocation sites and call sites as LC, LD1, LD2. and I start drawing my points to graph by transferring over each of these statements. So once again, because by virtue of the first statement, I say C0 can point to LC because I'm analyzing main in context 0. So C0 can point to LC. Actually, I should have said LC0. Okay. Then I transfer over this function call, and then I say B, because of this allocation new D1, the B pointer in context LD1 is pointing to L0D1. So L0D1 is basically the abstract object corresponding to new D1. LD1 is the allocation site, and L0D1 is the allocation site LD1 in the context 0. So that represents this abstract object D1. And then when I dispatch, then B can point to this object. So that's what B pointing to this means. But when I analyze B, I'm analyzing it in the call context of LD1. I'm doing a call context point analysis. So that's why a subscript B with its context, which is LD1. So B in context LD1 can point to LD1 in context 0. And then this function copy is just helping along this argument B to the helper. And let's say this call site is L helper, then D is being analyzed in the context L helper because we are using a call context depth of 1. And so I'm just looking at the call site. So D is being analyzed in the context L helper, and D just gets a copy of B. So whatever B LD1 was pointing to, DL helper will also start pointing to, and so I draw an arrow from DL helper to whatever BLD1 was pointing to, which in this case is L0D1. So this is the points to graph till this point. So far I have analyzed these two statements, and I have done the dispatch from helper B to base D. Okay, and this is the call context sense pointer analysis till depth 1 result so far. Okay, let's continue. So what helper is going to do is going to return D. D is being analyzed in DL helper, and that return value is going to get returned all the way back to X. So X will start pointing to L0, whatever DL helper was pointing to. So X will start pointing to L0 D1. So, and X was being analyzed in the context 0. So we draw an edge from X0 to whatever DL helper was pointing to, which is L0 D1. Okay. Now this was because of the transfer of this statement. I do a similar transfer across the second function call here, which is base B, the y equals c dot copy. And once again, I create a new abstract object for new D2, which is L0 D2. The allocation site is LD2 being executed in context 0. So that becomes L0 D2. This gets copied to B being analyzed in LD2. So BLD2 may point to L0 D2. This will again call helper, and helper will be analyzed in context L helper. So that means DL helper will get a copy of whatever B is holding. B is holding in the current context, and B in the current context is LD2. So whatever B LD2 may point to, which is L0 D2, now DL helper may point to. So DL helper may point to L0 D2 objects as well. Recall that previously we had said that DL helper may point to L0 D1 as well. So notice that this is an approximation, and DL helper it seems like there's only one D, which is DL helper, which can point to both D1 object or a D2 object, depending on which call it is. And this approximation is coming because of the bounded depth of 1. Okay, let's continue. Similarly, this is helper is going to return D all the way to Y, and just like X, just like we did with X, whatever DL helper may point to, Y0 may start pointing to. DL helper may point to both L0 D1 and L0 or L0 D2. So Y0 may conservatively also point to either of these. Once again, this is an approximation. We know by manually inspecting the program that Y0 can only point to L0 D2, but because we are doing this depth 1 context sensitive point analysis, we have to make this we had to make this approximation for DL helper, and because that gets transferred to Y, so Y0 seems to point to both L0 D1 and L0 D2. Now, once again, so this is not a fixed point. If I transfer again over any of these statements, then I will eventually get a fixed point which will require x0 to point to whatever DL helper is pointing to, and that would mean that x0 can now also point to L0 D2. And once again, notice that this is imprecise. Even though I'm using a context-sensitive pointer analysis, I get an imprecise answer because it seems like both x can point to either D1 or D2, so I cannot resolve the function, the virtual function called f at compile time. I'll have to resolve it at runtime. Similarly for y. And so this is imprecise, and even though I'm using a context-sensitive analysis. And the reason it became imprecise is because I just introduced another extra function call in my call stack, and that exposed the limits of my context-sensitive analysis, which was bounded at depth 1. On the other hand, if I had used a larger depth of my analysis, so if I had used a call context depth of 2, then it would have worked for this example. But then it wouldn't have worked for some other examples. For example, if I just created 2 helpers, then even a depth 2 wouldn't have worked. However, if I had used a full region-based analysis, which would have just summarized all the callee functions and kind of inlined them at all call sites, that would have all worked for arbitrary call context depths or call stack depths. But as we know, it can be very expensive, especially for large programs. So these examples basically demonstrate the capabilities and limitations of a context-sensitive analysis and how the depth parameter plays a role in determining the precision of the analysis.